Hello and welcome back to Joe Bailey Revision. Today this is the 7th chemistry video and it's on quantitative chemistry, which is chemistry which contains a lot of maths, and it'll be very interesting. I'll talk you through it. So, quantitative chemistry. So the first thing we've got to look at is the law of the conservation of mass. Basically what this means is that no atoms are lost or made in a chemical reaction. So because of this, the mass of the product of a reaction will equal the mass of the reactants. However, in some reactions, in non-enclosed systems, gas escapes, meaning its mass leaves a container, meaning this might not be shown. However, it's always true. Chemical reactions must be balanced. So this shows us like symbol equations. Symbol equations, you always got to balance them for it to actually make sense, for it to actually work as a reaction. So for an example of a balanced equation, this equation here, it's got C plus H2 turns to CH4. So a 2 has to be placed in front of the H2 to make it become H4. This thing cannot be created. You can't get 2 out of nowhere. So the 2 has to go there to double that to make it equal the result. So next, let's look at relative formula mass, also known as MR, or relative atomic mass. Relative formula mass of the reactant equals the relative formula mass of the product, meaning it stays the same in a similar way to normal mass, regular mass. So the sum of all atomic masses in a compound. So that means if you add together all the atomic masses of the numbers, you will get it. And it's the atomic mass is represented by the largest number on the element. And we always times the atomic masses by the amount of the substance that there is. So if there's this many of an element, we'll times it by that much. So let's have a look at an example. So here we've got aluminium 2 and O3. So the Al2, the atomic mass of aluminium is 27. But because we got 2 of it, we're going to times that by 2. And the atomic mass of oxygen is 16. And because we got 3 oxygens, we're going to times that by 3. And then we just add together these 2 calculations, which gives us 102. That means that 102 is the relative formula mass of these things. Meaning, if this was 2 things reacting into this, their relative formula mass, relative atomic mass, would be exactly the same, because it's the same for reactants and products, of course. So next, let's look at uncertainty. So there's uncertainty. Uncertainty is basically the degree to which a measurement would be unsure. So let's look at this. So for a single result measurement, uncertainty is plus or minus half of the gap between measuring points. So if we look at this ruler, the measuring points are all 1 centimeters. So there's 1 centimeter between every point. And because of this, we take half of it. So we do 1 divided by 2 equals 0.5. So plus or minus 0.5 equals the uncertainty. And this is because if we're taking a reading off here, we're rounding it up to the nearest 1, basically. So it could be 0.5 off because we're not taking into account those smaller values. Next, uncertainty plus or minus half of the range. So this is for a set of data. So if you've got a load of different values, you'd find out the range of it, which is the biggest value minus the smallest, and you'd half that. So if the range was 2, the uncertainty would be 1. That sort of thing. You just got to know how to find the range for this, really. And sometimes it'll ask you for the mean before of however many values, which can help in that sort of question. So next, quantitative chemistry. What's next? Moles. Which are measured in mole. So relative formula mass in grams, 1 mole of carbon weighs 12 grams. So this is basically a way of expressing the formula mass in terms of grams. And because 1 mole of carbon weighs 12 grams, if we remember looking at the atomic mass of something, that'll find out how many grams 1 mole of something weighs. So let's look back here. Aluminium we said was 27 on the atomic thing. Then that means that it has 27 grams is 1 mole of it. So we can always link these things together. It's very clever. 1 mole of any atom, ion or molecule equals the Avogadro constant number of atoms. So that means there's 6 0.02 times 10 to the power of 23 atoms per mole of any substance. So that makes it the same across all things. So you might need to remember that number. There's a equation involving mass, moles, and MR. MR, of course, being relative formula mass. Mass equals moles times MR, which can be rearranged into moles equals mass divided by MR. Let's look at an example of an equation where we use this, or an example, yeah. So here we got magnesium plus 2 hydrogen chloride, hydrochloric acid, whatever, turns into magnesium chloride plus hydrogen. So if we look at this, we look at the amount of moles in it, that's represented by the number at the start. So that is 1 mole. Those are both 1 mole. That's 2 moles because there's a 2 at the start. We only count the big numbers for the moles. That all play a big part later. And then we find out what the MR is. So that's all the ARs added together. So of course we've got 24 there because magnesium's 24 AR. Here we got 2 plus 71. That's because chlorine is 35.5 and hydrogen's 1, but we times them both by 2 because of the 2 in front. And the next bit, magnesium's 24 again, and chlorine is, we times it by 2 again because there's a 2 at the end. The little 2 at the end only means that, it doesn't mean the moles change. That's an important thing to remember. H2 is hydrogen 2, which means we times it by 2 gives us 2. Thing is, if we want to find the mass, we've seen earlier, mass equals moles times MR. So we just times these two together to figure out the mass. And this could be like a full question. So yeah, it's kind of useful. So we times those two together, 24 times those. Yeah, those are all obvious. The only one that's slightly confusing is where we times together the moles of the moles and MR of the bit with the 2 moles because it's times that by 2. And we can figure out whether this is correct as the mass of both sides should equal the same. So the total mass of this side is 97 and the total mass of that side is 97, meaning it's worked correctly. So next, let's look at concentration. So what is concentration? Concentration is basically the amount of something that is in a certain volume. So something's more concentrated if there are more particles in the same area. So if we look at these diagrams, that thing there is dilute and that thing there is concentrated. They're the same size, but the concentrated one has got more in the same space. That's what it's all about. And concentration equals mass divided by volume, or moles divided by volume, and that's how you can figure it out. And a thing that's normally used for volume is a decimeter cubed, and that equals 1,000 centimeters cubed, and you might have to convert that in an exam or something. I just realised we missed over here the bit about limiting. So limiting the quantity of one reactant limits the amount of product that can be formed. The product being in mass, moles, or grams. So next, let's look at percentage yield. Percentage yield is the actual yield divided by the theoretical yield times 100. The actual yield is the actual amount of product made, and the theoretical yield is the maximum product possible. So when things actually happen in a reaction, a lot less tends to be made than you would think would be possible, because things hold it up. So let's look at this. Very few reactions have 100% yield because raw materials may be impure, which would lead to a smaller amount. Some products may be left in the apparatus, which would lead to a smaller amount. Wasted materials that are unexpected may be there and change things up from what we were expecting in the first place. So next, let's look at atom economy. Of course, this times is by 100 because it's a percentage. Percentages are always times by 100. Always remember that part. So next, atom economy. Yes, the mass of wanted products is a percentage of the total mass. So this is really about finding how much useful stuff we're getting. So the mass of the useful product divided by the mass of all reactants times 100. And of course, we've said that the mass of the reactants is the same as the mass of the products, which is highly important here. A higher atom economy increases the efficiency of making something and decreases the waste, meaning it's good for the environment. And also it's good for business because you're making more stuff out of a smaller amount. Check my business videos, yeah. Yeah, of course, massive useful product divided by massive reactants times 100. So that's how we can figure it out. So yeah, next let's look at the volume of gases. 1 mole of any gas has a volume of 24 decimeters cubed, which is very specific. This is at room temperature and at a normal pressure. So through this we can find that volume equals 24 times the moles. So this means that if we want to find the volume of a gas, we can just do 24 times the amount of moles if we know the amount of moles it has. Also, we can twist this around so that volume divided by 24 equals the moles if we don't know the moles. So then we can cleverly use this equation, because sometimes they'll put it together with the equation on moles equals mass divided by mR. Sometimes they do questions with 2 stages, and this would be good for using in that and what you'd have to do. So yeah, that's great. Thank you for listening to Quantitative Chemistry. That's very good. This is a paper 1 topic. I'll remember to say that at the end of all my videos now. And basically I've gone through everything I've done so far and sort of checked where it is, and I'm slowly going through this list to try and get everything covered. So there we go. That's Quantitative Chemistry can now be crossed off, and thank you and goodbye.